So this presentation is going to be in English, but if I'm going too fast, then you can tell me and I'll slow down a little bit. And if you have any questions, you can just ask me in the middle of the slides. So our presentation is going to be about my work in CVPR 2017. It's noise-robust depth from focus using a ring difference filter. So there's going to be some extra material that has not been on the paper in CVPR because this has also gone into a journal. And so I'll briefly describe some of the stuff that's in here. So what you're looking at here today is a lot of the cell phones nowadays are coming out with, a lot of the high-end cell phones are coming out with dual cameras. And what that allows you to do is to use some computer vision or image processing to actually acquire depth information of that image. And using that depth information, you can also do different applications like synthetic defocus, which is the prime sort of goal of our approach. But trying to make it accessible for cell phone users so that it doesn't have to take a long time, or it doesn't really have to require some sort of dual lens system. Because when you're looking at a cost of the camera itself, usually it takes around 10% of the entire manufacturing cost to add that camera. And when you have two of those cameras, it's probably going to be much more expensive than that. And so what you want to do is actually provide different kinds of applications without having to constrain yourself using hardware. And so there have been a lot of different single camera depth estimation. And one of them is actually the Google Camera app. And what it uses is the motion of the camera to estimate a stereo image. And then using that image, you can actually find the depth, and then it'll defocus that image for you. But it doesn't actually work that well because your motion actually has to be perfectly in line with what they want the stereo image to be. So it has to be very slow. The objects can't be shiny. The objects can't move a lot. And it's actually kind of bulky. You actually have to capture around 3 seconds of video. And then after that, there's a processing that goes on the cell phone itself. But overall, it's very unstable. And the structure from motion effect is where you have a stream of video that has a very small baseline, so that the cell phone, you don't have to actually move around that much to actually generate that stereo effect. And what you get is a very high quality depth estimation, but this takes a long time, so around 20 minutes on a computer, or maybe up to 30 minutes. And it's also very, so the bottleneck here is actually the software, because the cell phone can't actually handle that kind of computation. And also the biggest constraint is the RAM, because you actually have to optimize for all variables that you have. And that's actually not that easy on a cell phone. So here are some of the target examples that I was looking at. So the first one is work done from a guy from the University of Washington. And he worked with Google to get this paper out. And this is the prime target of my paper. So it was a CVPR 2015 paper that actually uses defocus to measure depth estimation. And using that, it'll generate a metric depth of the scene. Now, because metric depth is such a computationally heavy algorithm, what they actually did is try to relax the problem. But even after relaxation, the algorithm requires around 20 minutes to generate that kind of depth. And what I try to do is to relax that rigorous depth estimation using blur, and try to make it not metric, but actually relative depth, so that you can actually use it for simple applications like defocus. And the one on the right is done by Samsung, and it's more of a segmentation problem rather than a depth problem. When you take a selfie, the person in the image can be detected using deep learning. And then using that information, you segment out the person and then blur out the background to get this defocus effect. So our objective is to lower the computational complexity of the entire algorithm and work independent to the type of camera that you have. And also it has to be robust to environmental constraints like noise. So the main contribution of my paper is the use of the ring difference filter, what we call the ring difference filter, or RDF from now on. And it's a robust focus measure that measures focus in a position in the location of a pixel so that you can actually compare the focus between different images and see which one is most in focus. And by using that information, you can actually estimate the depth in terms of the image label or the image index. So if you have a video that goes in sweeping the focuses, then you can, if you know the direction of that sweep, then you know which image is most in focus, and therefore which is at that location. Now, it's not metric, but it doesn't have to be for the kind of applications that we're looking at. And also, we developed this efficient depth from focus pipeline that actually synergizes with the focus measure and its characteristics, and therefore we can get a fast speed up. So this is the kind of input that so that's the focus sweep that you get. And this is about, I think, 0.6 seconds of just a sweep. This is captured on an LG V10. It allows for manual focus using video. And using that, you can see the type of noise level that we get from a low-lit environment. And using these noisy data, we're trying to get relative depth estimation so that we can use it for other applications. And the kind of results that we get is something like this. So in previous attempts, the CVPR 2015 paper actually requires this kind of pipeline. So first, you align all the images so that they look the same. And then you use a focus measure to actually measure the focus of each pixel in each image. And then using graph cut, you optimize for what the depth looks like using the response of the focus measure and constraining it so that nearby pixels have the same depth, but not when they encounter a boundary. And the biggest bottleneck here is the graph cut optimization. Because graph cut is not a polynomial algorithm, it actually doesn't scale well when you increase the image. If you look at the paper that they wrote, they say that they used a 640 by 360 image, 25 of those images to estimate that depth that I showed before. And it takes around 20 minutes to estimate it throughout. What we propose is to change the focus measure so that it synergizes well with the next step. And instead of using graph cut, we use something that is more efficient called cost aggregation. Now, cost aggregation is used very widely in stereo matching, and it's an optimization method for the actual response itself. It'll refine the response of the focus measure. In this stereo matching case, it'll be the disparity. And what we do is we refine the response of the focus measure and then use that as the estimation. And this takes around 6 seconds with the same kind of parameters that they use in the 2015 paper. So what is this focus measure? Let's start with an overview of what exactly focus measure is. So if you look at a simple thin lens model, then you can see that when the focus is just right, the light source is actually focused onto the CCD in a little point. And if you're moving away from that focus setting, then you get larger and larger image blurs. And this is what causes different effects like bokeh and blur.
So you said that using the same parameters, you have a 200 times speed up. But if you use a larger, higher resolution picture, is it still 200 times or?
The speed up will be that much greater because graph cut is actually NP. And so what happens is the time it takes for that optimization to complete goes exponentially large. So for cost aggregation, I don't know what the number was off the top of my head, but it was a few seconds, I think, something like 2 seconds to run. Whereas graph cut, for their purpose, runs at around 45 seconds, if I remember correctly. So that's already a big disparity, but as long as the image size increases, you get that much more. And also because if you increase the image size from 640 to 360, it doesn't increase just to full HD because you have multiple photos. So therefore, 25 times that increase. and that will actually impact the algorithm working. So there are various types of focus measures out there. So there are most of them are gradient-based, but some are statistics and wavelet or frequency domain-based. But our approach is in the gradient space. So actually calculating the gradient, but calculating it in such a way that is suitable for the algorithm that we're going to use. So this is the most common gradient estimator. This is the Laplacian filter. And what we did is create the filter on the right, the RDF, which looks like a donut with a little center. So when you look at a conventional Laplacian filter, what it does is actually measure the focus, the gradient between the center pixel and the pixels right around it. And what happens is you get a frequency, the response like this. So as the points get more yellower, then they have a higher response. Then you can see that the result is kind of noisy. So all the other spaces are actually, they have a response, and the response is actually comparable to the high responses that you should get. Whereas the focused region over here and the dice is where you should be looking at, but all the other values also have a pretty high response. So what we thought is maybe because this is a noise. And so what we did was increase the size of the filter. So this is what we call the naive filter, so naively increasing the size. And that causes it to be noise robust. And it actually does produce a greater response, a more clean response. But we found out that this doesn't actually translate well to the cost aggregation afterwards. And there was still more work to be done. And we thought maybe if we increase the confidence of each measurement, so the response looks, if you have 30 images, then the response has 30 points. And the shape of the response actually determines how cost aggregation will work afterwards, because the shape of the response is going to be copied out to pixels around that center pixel. As long as it's high confidence, then the right type of shape will be overwritten more. So it'll propagate more. And if you have a low confidence, then it'll propagate less. And so why don't we try increasing the confidence by just padding the filter with zeros? And we call this the resized Laplacian. What it does is intuitively, it tries to resize the image to half its size to suppress some of the blur that you have due to the lens blur. And what it does is actually, in a high-level sense, it tries to suppress the blur. And then if it's still blurry, then it can confidently say that it is a blur and not in focus. And this does get a cleaner response, so you get a more localized response. But we decided that it was actually beneficial to have that noise robustness. And so by combining the two, we get something like the RDF. And this has a better response. It has a stronger response, but also a cleaner response in the same time. And we can see from the toy example here, the red point denotes the location that we're looking at. And all these images here are differently focused, so they all have different amounts of blur in them. And you can see as the correct response should be maximum at number 16. So where the image is most in focus should be number 16. And Laplacian looks actually pretty noisy. And naive does try to smooth things out, but it still is unable to suppress all of the responses because it's not as confident. Resized Laplacian is much more confident, but it still recognizes noise as a type of feature, and therefore it tries to balance the two out, and ultimately it fails in certain places. And RDF is allowed to get that clean response, and this is very important for the next step of our algorithm. So you can see the results for our measurement is here. The red pixels are pixels that are incorrect. Basically, the incorrect responses are marked in red, and the other responses are marked in white and black. And so you can see as noise increases from the top to the bottom, you can see with the visualization here, the noise gets pretty intense in the bottom row. And you can see some of the other, so these aren't the the filters that I've been mentioning up till now, but these are actually benchmarked. So they have been benchmarked by a paper in PAMI, if I remember correctly, and or TIP, I think. So they basically benchmark different types of focus measures, and they determined that modified Laplacian and wavelet are the best in general. But then eigenvalue is best for noisy types of data. And so by having that structure, we can get high quality responses, even though the image is noisy. So the pipeline overview is going to be next. The initial depth estimation of the image that we saw in the very beginning of this slide is something like this. So with RDF, you get a very sparse sort of estimation, because the places where you find focus information the most are the edges of the image. So those edges are more correct, and all the other regions, the homogeneous regions, are going to be more noisy, and they're going to be incorrect. And to remedy this, we aggregate the image. So cost aggregation actually refines the response volume, and it creates a more clean, better formed response. But you can still see there are some errors here. This is due to what we call bokeh. So bokeh is the little high intensity light positions where it actually reflects light. And that reflection causes a big blur that the focus measure actually thinks is an edge. So it'll look at that blur and it'll think, oh, that's moving in size, so that's probably going to be an edge. And so in the 2015 paper, what they did is actually use optical flow on all the images and see how the light converges on one spot. And by determining how many points converge into one spot, they can detect bokeh. We take a much simpler approach by basically converting all the images to black and white, and then seeing how the intensity changes at different positions. So if the intensity changes a lot, then we can definitely tell that, oh, this is going to be bokeh because the light is increasing in size, and therefore causing it to think that the intensity suddenly changes at certain image labels. So using that, we can detect the different types of bokeh on this image. And also, we used another confidence mask. So basically, using the response of the aggregated results, you can actually determine if it's confident or not. And if it's not confident, then you reject those positions and then refine them afterwards. Those masks together look something like this. And then the mask is applied on top of the results that we get from the aggregated result. And once the holes are made, we use non-local filtering. So basically generating a tree over the entire image and then propagating out values on the path of those trees. And we get something like this. So here are some of the results. This is a comparison between our approach and the 2015 approach. You can see that the 2015 approach actually has metric depth. So it's a more metric estimation of depth. But you can see it's also very blurred out, and it actually has some noise that it follows and thinks that it's an actual structure. Whereas our approach is more quantized, but it's sharper, and it actually retains a lot of the information that you get from the image. Here's another example. Look how the bottle has a lot of holes, and you can actually see the boundaries of each bottle, whereas the other one, it's a very gradual change, because what they do is they try to optimize globally for all the parameters in the pixels. This is one of our examples of a low light situation. This actually is captured by a DSLR, and we used around 120 images. So you can actually see RDF is able to actually get that gradient, that smooth gradient, if you use a lot of images. Whereas other focus measures, they fail in certain ways where maybe it's due to noise or confidence. They actually get overwritten by other labels, and you'll see holes in these regions here when there's very gradual sort of depth changes. And this is another low light example. You can see that we get a lot of these fine structures, which would be hard to get with some sort of global optimization, because they'll try to reason with every pixel and find a consensus. rather than just trying to look at the local patch itself. Here's a stylization example where using the depth as guidance, we repaint the image in different colors, and this is the result. So that is it, and if you have any questions, then you can ask me now. And also the code is going to be up on my website, but as soon as the journal paper goes through, then I'll try to get that uploaded as fast as possible. So thank you.
지금 이제 그 뎁스 인포메이션을 구하는 게 기본적으로 아까 뭐 듀얼 카메라가 있는 스마트폰을 말씀을 하셨는데 일반적인 스마트폰에서는 어려운 상황일까요? 아니면
스마트폰에 카메라가 한 대만 달려 있으면은 좀 힘들더라고요. 그게 여기 있는 예제들이 다 이제 카메라 한 대를 가지고 하는 메소드들인데, 근데 일단은 핸드폰에 돌리기에는 계산량이 많고요. 대부분 다 계산량이 되게 많아요. 그 구글에서도 한 것도 계산량이 굉장히 많은데, 그거를 이제 좀 간단히 해서 좀 뎁스가 이상하게 나와도 그거를 취급하는 정도로. 그리고 근데 구글에서 하는 것도 이제 그 사이사이에 모션을 에스티메이션 할 때 그 핸드폰 IMU가 그렇게 정확하지 않아서 이미지를 통해서 그 모션을 에스티메이션을 하는데, 그 이미지를 통해서 하면은 옵티컬 플로우 같은 방법을 쓰고, 옵티컬 플로우를 이제 제대로 하려면은 그러면은 컴퓨테이션이 되게 많이 들어가고요. 그게 만약에 아니라면은 그러면 이제 놓치는 경우가 많죠. 이렇게 움직이다가. 그래서 하나로 하기는 힘들고요. 그리고 카메라가 두 개여도 이제 핸드폰에서는 카메라 사이 간격이 굉장히 좁잖아요. 그것 때문에 이제 에러가 굉장히 많이 생기는 경우가 많아요. 그래서 두 개로 해도 그렇게 막 쉽게 되는 그런 프로블럼이 아니에요.
근데 아까 이제 어쨌든 카메라 두 개가 있는 경우에는 그나마 이제 뎁스 인포메이션이 있으니까
그쵸.
그 아까 이제 프로세싱 타임을 뭐 몇 초대로 이렇게 줄일 수 있는 거고, 이제 하나짜리 그 스마트폰으로 하면은 뎁스 인포메이션 자체를 구하는 게 또 시간이 걸린다는 말씀이시죠.
그쵸.
예.
감사합니다.